Assalamualaikum warahmatullahi taala wabarakatuh and good morning. I'm Dr. Sabah Bau from the Physics section, Pusat Pengajian Pendidikan Jarak Jauh, University Sains Malaysia. This is course JIF 318 Quantum Mechanics. We are in chapter 1, Introduction to Quantum Physics. This is segment for unit 1.7, the wave nature of matter. The objective of this lesson is hopefully after this lesson you will be able to explain the proposal by de Broglie on wave matters and to compute the de Broglie's wavelength of matter. There is a spelling mistake here. It should be G here, not F. Okay. In the previous segments, we had discussed how light exhibit both the wave and particle properties, what we call as wave-particle duality. So wave-particle duality leads to a more radical idea. If light can exhibit both wave and particle properties, what about matter? Matter is made up of particles, atoms, molecules, and so on and so forth. So particles made up, matter made up of particles. So if light can exhibit both wave and light and particle properties, what about matter which consists of particle? Can particle exhibit both wave and particle properties? Louis de Broglie, a Frenchman, made a startling proposal. Matter which is composed of particles may also behave like a wave. Of course, particles have particle properties. And de Broglie's proposal was, what about if particles also have wave properties? He proposed using the relationship between momentum and wavelength, appropriate for a photon, and applying it to matter. Photon, the energy of photon, as we had discussed previously, equal to h nu. H is the Planck constant, nu is the frequency. Momentum is for particle, P equal to mv, where m is the mass of particle, v is the velocity. For a photon, it has no mass, therefore, according to the momentum equation, photon shouldn't have momentum. But here are the proposal between the wave and particle from the Broglie wavelength. So, if a particle have wave properties, de Broglie suggested that it should have this relationship. This means P, momentum, is for particle, and it should be related to lambda, which is the wavelength of a wave. This proposal seems absurd. Why absurd? Does my body behave like a wave? We as human beings, when we see this equation, the question is, do I emit wave? Or I will be diffracted every time I walk through a door? Because in wave, if the wave pass through a small opening, then diffraction occurs. What about we as human beings passing through a door? Does we produce diffraction pattern? And forms an interference pattern when I walk through a room with two doors. Also, initially when de Broglie suggested these wave properties of matter, people ask about this. A wave, for example, in Young double slit experiment, when it passes through two slits, then you have interference pattern, dark and bright fringes. What about particle when it passes through two doors, for example? Does it have interference pattern? So here is an example. to determine the de Broglie wavelength of a walking man. Consider a 70 kilogram human being, it's a normal human being, walking at 1 meter per second. So, assuming that when we walk, the speed of our walking is 1 meter per second, so we can calculate the momentum P equal to mv, which is 70 kilogram meters per second. Then by using the de Broglie wavelength, we can calculate actually the wavelength produced by a walking man, which is equivalent to 9 multiplied by 10 to the power of negative 36 meter. That means there is a wave, but you can see here that the power is 10 to the power of negative 36 meter. So this is a tiny wavelength, very, very, very short wavelength, even to atomic or nuclear scale. Atomic scale, maybe it is about angstrom, okay, which is 10 to the power of negative 10, and nuclear scale, for the nuclear, it is 10 to the power of negative 15 meters, or 1 Fermi. It's about that size. So if 10 to the power of negative 36 here, it is much smaller than the nuclear scales. So cannot be observed. The instrument we have at the moment, we cannot observe lambda for 10 to the power of negative, or in the order of 10 to the power of negative 36. That's why we cannot observe if a man walking. We cannot use at the moment, we cannot use any instrument to measure the wavelength generated by a human being walking at 1 meter per second. Okay? When we cannot observe, it does not mean that there is no de Broglie wavelength. Yes, from calculation we have, but it is very, very tiny, that even using the most sensitive instrument at the moment, I said at the moment, in the future, some of you might be able to fabricate a detector which can detect this 10 to the power of negative 36 meter wavelength. So, how to observe de Broglie wavelength? Using the present situation, present instrumentation. So, to see the effect of matter wave, it is necessary to conduct an experiment in which the wavelength is significant to the size of the physical system. That means, if we want to measure de Broglie wavelength at, for example, like 10 to the power of negative 15 meter in the nuclear size region, then we should have physical system that of the same size, 10 to the power of negative 15. So in the nuclear system, we have this size, or in the atomic system, we have atoms, okay. To maximize lambda wavelength, P, which is momentum, should be as small as possible. Remember that lambda is inversely proportional to momentum P. So, in order to easily observe lambda, we should have P as small as possible. Okay, P is M multiplied by V. M is the mass and V is the speed. So either M should be small or V should be small, or both should be small. Okay. For a non-relativistic particle, that is when the particle is moving not at the speed or almost at the speed of light, we have this relationship P equal to Z to ME, where M is the mass of the particle and E is the energy of the particle. Okay, this relationship can be obtained, okay? E equal to half mv squared, P equal to mv, so you can rearrange these two equation of momentum and energy, then basically you can have this relationship. At fixed energy, M should be as small as possible. So if E, just now we said that P should be as small as possible. So if at fixed M, at fixed energy E, if E is fixed, then in order to get small momentum, M should be small. Okay. This makes the electron a convenient particle to use. So electron is the quite easily available particle, the smallest, even though we have elementary particle. We are talking about the normal macroscopic particle. We have proton, we have neutron, and we have electron. So electron is the smallest. So we can use electron to observe this de Broglie wavelength. In order for the electron to behave like waves, they must be scattered through an aperture. Remember that aperture, like slit, with a size comparable to or smaller than their wavelength. Just like in light, in order to observe the interference pattern, Young double slit experiment, the slit should be very small. Okay. So here the aperture, even though we do not have physical slit, but the most important thing, the size in order to scatter this electron should be comparable to or smaller than the wavelength to be observed. This can be achieved by scattering electron from a crystal lattice. So crystal lattice, we have this size about the crystal lattice distance is about 10 to the negative 10 meter. That's in angstrom. So Davison and Gemmell scattered electron of a nickel sheet and measured the intensity of the scattered electron as a function of the scattering angle. He observed interference pattern, which can be explained by taking the electrons to behave like wave. If you look through some of the text on textbooks or even on internet, you can see or observe the interference patterns by electron is similar to the interference patterns of light or X-rays in crystallography using crystals. Okay, so in crystallography, people use X-ray and see this scattered pattern. If we use electron, we can still see the scattered patterns. So electron undergoes scattering. So the scattered pattern here is similar to wave properties. Not only for electrons, it was proposed for all matter. Basically, if electrons have these wave properties, then since all other matters, when we say matter, it can be solid, liquid, or gas, whatever is around us. All other matters also have particles inside it, composed of particles. So the proposal was not restricted to electron, but is for all matter. So there is a symmetry between radiation in the form of wave and matter in the form of particles. Both can be considered to behave as both particles and wave. So in radiation or light or X-rays, we said that these radiation have wave and particle properties. The same thing for matter, which consists of particles. So matter have these both particle and wave properties. As a conclusion, de Broglie proposed that moving matter emits waves. Consequently, now both radiation and matter have both particle and wave properties. Thank you very much for your attention.